Okay, so last section we're going to take a look at is 7.2. We're going to end up splitting this into two sections, which means we're not going to get to the second half of this section for a while. All right, because next week you have shot. The next week after that is the midterm, and the next week after that you have shot, and then the next week after that is when we'll get to 7.2 part 2. Luckily, part 1 and part 2, you don't have to really remember a lot to be able to do part 2. So if there is anything, I'll remind you. We'll do like a warm-up that day, just to remind of what we're going to do right now. But we should be okay. All right. So first of all, in general, what does it mean if a function is an inverse? Well, visually, it means it's a mirror image. A mirror image over the line y equals x. So let's say I had the square root function. What's the inverse of square root? Yep. Squared. So if I graph x squared, right, and I'm just going to graph it when it is greater than or equal to 0. And then I'm going to graph square root of x. And then I'm going to graph the line y equals x. And you're going to see that they are mirror images. So that's just half of a parabola. And we wanted to graph the positive part. That's a square root function. And here's the line y equals x. It's kind of hard because I didn't zoom in a lot, but if you were to fold this on that black line, the graph in blue would land on top of the graph in red because they are inverses of each other. And that's true for any two graphs that are inverses. They are mirror images over that diagonal line. Now, for a function to have an inverse, it has to pass the horizontal line test. Right? We know we've used the vertical line test. That's different. The vertical line test is used to tell you if what you're looking at is a function. If a vertical line hits it more than once, then it fails. A horizontal line test is used to tell you if the inverse of what you're looking at is a function. Now, think about the graph of sine. It looks like that. If you draw a horizontal line there, anywhere you want, would it pass the horizontal line test?
Oh, no.
No. Because I could put a horizontal line somewhere and it would hit more than once. The problem with it hitting more than once is that if I asked you a question about inverse sine, you could give me an answer here, you could give me an answer here, you could give me an answer here, you could give me an answer. You could give me an infinite amount of answers. The problem is we only want one answer. So what we're going to do is we're going to make it so that graph passes the horizontal line test. And the way we do it is we're going to block out most of the graph. And we're going to focus on a specific section. So basically what we're going to say is, no, the whole graph of sine doesn't have an inverse, but this small section does. And that's how we're going to do it. And that's how every book, every calculator, when you do inverse trig, that's how they all work. Okay? They focus on a small section. So let's say I focus on that section. Does that section pass the horizontal line test?
Yeah,
No. Horizontal line could still hit more than once. How about if I focus on, that's pretty close. How about that section?
Yeah.
That section passes the horizontal line test. Okay, so focus on what that looks like. So let's move this out of the way. Oh, it's actually perfect. We're focusing from here to here. That's basically a quarter cycle to the right and a quarter cycle to the left. What's a whole cycle in sine? From 0 to pi. 0 to pi is a half cycle. 0 to 2 pi is a full cycle. So that's a quarter cycle. you've gone up. That's all you've done. If 2 pi is an entire cycle, how much is a quarter cycle? What is it? Yeah, pi over 2. So what we're going to do when we do inverse sine is we're going to restrict the domain of the original to only look between negative pi over 2 and pi over 2. By doing that, we are forcing the graph of sine to pass the horizontal line test, which is what we need to have. Okay? Now, you might be saying, well, aren't there other sections you could look at that pass the test? Absolutely. You could look at this section right here. But nobody does that. Okay? Every calculator is programmed when you do inverse trig to look at the section between negative pi over 2 and pi over 2. That's the section that everybody agrees to use. So, the solution to our function not passing the horizontal line test, I just told you guys this, restricts the domain to be from negative pi over 2 to pi over 2. Now, earlier I said to you, anytime you draw an inverse, it's a mirror image over this line. What line did I say it was a mirror image over? Y equals x. Think about what y equals x means. Okay? Like if I said y equals 2, and then I said something like evaluate, and I gave you the expression 3y plus 7, that means you take the value that y is equal to, and you plug it in for where you see that letter, and you do out the arithmetic. Well, what this means is wherever you see a y, you could replace it with an x. Or you could think of it the other way. Wherever you see an x, you could replace it with a y. Okay, that's what that really means. So think about that in terms of domain and range. If y's, when you do an inverse, y turns into x, x turns into y. So what do you think it's going to do to your domain and range when you look at them in the original, and then when you compare them to the inverse? Want to have a guess what's going to happen to your domain and range? Yeah? Domain and range flip. Yep, they're going to flip. The domain in the original is going to become the range in the inverse. The range in the original is going to become the domain in the inverse. Domain and range switch places. So let's go back and look at this graph. We know the domain of the original is negative pi over 2 to pi over 2. What's the range? How high and low does the sine function normally go? It normally goes negative 1 to 1. The range of the original is negative 1 to 1. That range is going to become the domain in the inverse. Negative 1 to 1. Okay, let's go back up. In the original, we restricted the domain of the original to be negative pi over 2 to pi over 2. Well, the domain is going to turn into the range in the inverse. Okay, so domain and range just switch places. Now let's graph it. So inverse sine is not a graph that goes on forever. It's going to be trapped in this area between negative 1 and 1. Okay, I went a little bit bigger, so my graph's not on the edge of the screen. And negative pi over 2 to pi over 2. Pi over 2 is 1.57. Let's go a little bit bigger. Let's go negative 2 to 2 again. Right? So I did negative 2 to 2 on everything. And let's type inverse sine. If you got anything else, just get rid of it. Inverse sine. And before I tell you why that looks wrong. Negative pi over 2 and pi over 2, what's my units on that?
Radians.
Radians, I'm in degrees. If you wanted to do it in degrees, you could, but you'd have to say negative 90 to 90. Okay, so I meant to do it in radians. So put it in radians, and now you'll see exactly what it looks like. That is the graph of inverse sine. That is a mirror image of that section right there, over the line y equals x. Okay. It's kind of hard to see. I think with the parabola and the square root, it was easier to see. This is harder to see the mirror image because a lot of this is almost right on the line y equals x. If you put the line in there, all you're doing is mirroring that. You're doing a mirror image of that black section over the red section. Well, a lot of the black section looks like it's almost right on the line. If something's right on a fold and you fold it, it stays right where it is. But notice this part kind of curves down towards the end, and then when it mirror images, the curve gets kind of flipped up. Here, this curve is kind of starting to curve up a little bit. When you mirror image it, it starts to curve down instead. Okay. So that's the graph of inverse sine. Okay. Now, let's think about cosine. What does the graph of cosine look like?
Similar to...
Yeah, it's very similar to sine.
It starts at 1.
Yeah, it just starts here, and it goes more like that. So, does the graph of cosine pass the horizontal line test?
No.
No, it fails it, just like sine did. So let's put up a graph of cosine. And in order to get around that problem we had last time, we said we're going to limit the domain from what to what in the original?
Negative pi over 2 to pi over 2.
Let's try that here. Let's see if negative pi over 2 to pi over 2 works here. Here's negative pi over 2. Here's pi over 2. If you just look inside those red lines, does your graph pass the horizontal line test? Yeah. No. So negative pi over 2 to pi over 2 doesn't work this time. But what does work is that. Look inside that section. That passes the horizontal line test. Anyone think they can tell me what I just limited my domain to be? I basically just shifted it over a little. So it's not negative pi over 2 to pi over 2. It's now
0 and pi over
0 and pi. Yeah, because think about it. That's a full cycle. You're halfway through. So 0 to pi. All right? So if you restrict the domain to 0 to pi, you can make the inverse work. Okay? Now, I just said the domain is going to become the what in the inverse? Yeah. The range. So when I do inverse cosine, the range is 0 to pi. And the domain, well, if you get stuck thinking about it, like, wait, he wants to know the domain of the inverse. So think of the range of the original. The original looks like this. Well, more like this. Same idea. That goes from 1 to negative 1. The original range. So that becomes my domain. Okay, let's think about inverse tangent. Let me graph regular tangent, and we can see what that looks like. What's different about this graph compared to sine and cosine?
It's not continuous.
It's not continuous. Why not? At each discontinuity, you have a what? You have a vertical asymptote. Keep that in mind. Vertical. When we do the inverse, what do you think you're going to have?
Horizontal.
You're going to have horizontal asymptotes. So all the y's turn into x's, all the x's turn into y's. Right? So look at the range of that function. How high and low does it go? Infinite. The range of the original becomes the domain in the inverse. So what happens with inverse tangent is it doesn't go up and down forever. It goes left and right forever. Now, we need a restriction, right? Look at that graph. Does tangent pass the horizontal line test?
No.
No. If you put a horizontal line in there, it hits it a bunch of times. The solution? Let's limit it from negative pi over 2 to positive pi over 2. But can we include negative pi over 2 and positive pi over 2 this time? So negative pi over 2 would be right here. Can we include that?
Yeah.
Sam, you're saying no?
Yeah.
How come?
Like that. It's gonna touch. Each line would like touch it.
Well, the reason why we can't include it is because the curve never touches it. Because it's a, what? Yeah.
Asymptote.
It's an asymptote. Negative pi over 2 is an asymptote. Positive pi over 2 is an asymptote. So when you write the range, you can't include it. That's why I use parentheses. Okay? Now, the whole reason why the domain and range, why I'm showing you what it is because we're going to look at transformations. So if I say to you, all right, take inverse cosine and shift it up 1. Tell me what the new range would be. Well, if you don't know the original range, you're not going to be able to figure out the new one. Okay? So you're going to need those for what we do in a second. All right, so yesterday, yep.
Just gonna get the asymptote.
Okay, so yesterday we were solving right triangles, and we had problems like this. We get to a situation where we got that far in the problem, and then what did we have to do on each side to get theta by itself?
Take the inverse of her. Yeah.
Do what?
Take the inverse of it.
Yes, take the inverse sine of what's on each side. And all I said to you, without really explaining a ton, going into super detail, is that these cancel out. Well, they do cancel out, but only some of the time. Inverse sine and regular sine cancel each other out, and the formulas I'm about to give you are going to show you when they actually cancel out. And then I'm going to ask you why I didn't have to explain what I'm about to right now yesterday. It wouldn't have mattered. You didn't need to know. I just said, oh, just cancel them out. Don't worry about it. Okay? Then I'll ask you why I said that after I show you this. So, there's two different formulas. You can have, and if you look at them quick, you might think they're the same, but they're not. One of them has the inverse on the outside. One of them has the inverse on the inside. The kind of things we were doing yesterday, the inverse is always on the outside. Okay. When is the inverse on the inside? That's a different kind of problem. We haven't really looked at that yet. Okay. The inverse was always on the outside. So, this formula is saying that inverse sine and regular sine will cancel each other out. I wouldn't write that in your notes, then you won't be able to read them. But they will cancel each other out. And the answer that you get is whatever is sitting right there, as long as you plug something in between negative pi over 2 and positive pi over 2. Now, what's that in degrees? I'm trying to give you a hint at why I didn't have to explain this yesterday. What's negative pi over 2?
Negative 90.
Negative 90. And what's pi over 2? 90. So this was the one that we used yesterday when you had to do inverse sine. And I said, just cross them out. They just cancel. Don't worry about why. But how could you know that they're going to cancel? How come they would always cancel out yesterday? How come there wouldn't be a situation where they would not cancel out? Think about when we took like an inverse trig function of each side, we were solving for what? Why did we have to do inverse trig on each side?
Angle.
To solve for the angle, yes. The angle in a what?
Triangle.
In a triangle, okay. So we were solving for an angle in a triangle. Anyone tell me more about angles in a triangle? Yeah?
They have to add up to 180.
Okay, what else based on that?
If it's a right triangle, then the two angles can't be. Those two have to add up to 90.
Which two have to add up to 90?
The two that aren't already the 90.
Yeah, angle 1 and 2 in that picture would have to add up to 90. So what does that mean about each of the angles individually?
They're less than.
They're always less than 90. In order for this formula to work, the angle has to be less than 90, less than or equal to 90. That's what this is saying. Well, yesterday, the angle was always less than or equal to 90. It had to be, because you were dealing with a right triangle. That's why it wasn't important for me to tell you this condition, because I knew you would never be getting an answer that wasn't between negative 90 and 90. In fact, I knew even better, I knew you would never get an answer that was always positive. It would always be between 0 and 90. Yesterday. Okay. So, if we pick, let's just pick another random number. That's negative 1.57 to 1.57. So let's pick 1.2. Let's do the inverse sine of the sine of 1.2. Sure enough, works fine. Let's try a number that's not between negative pi over 2 and pi over 2. Let's pick 3. Okay, so let's do this inverse sine of the sine of 3. You get an answer, but you didn't get back the same one you started with because you didn't follow the condition. You went bigger than you were supposed to. Okay? Formula 1b is the same idea, except the inverse is on the inside. Okay? Somebody give me a number for x that would satisfy the condition for this formula to work. Chris? 0. So sine of the inverse sine of 0, when I hit enter, what should I get? I do. I get 0. Now, somebody give me a number that doesn't satisfy that condition. Eric? 3. This time, when I plug it in, it's not that I get a different answer back than what I started with, like up here. I don't even get an answer back. You can't even do that. Okay. All right, let's look at formula 2a and 2b. Now, what I want to try to show you is the pattern for the condition you have to follow. Okay? So you should be able to figure out what the condition is for each of those. There's 2 ways you can think about the condition. It's either the domain of the original, or you can think of the range of the inverse. Either way, it's going to be the same answer. The domain of the original. Let me just go back and show you. Domain of the original, negative pi over 2 to pi over 2. Range of the inverse, negative pi over 2 to pi over 2. That's where that condition, negative pi over 2 to pi over 2, comes from. So, when you're trying to think of the condition, just think of Finding Nemo. Or not, Dory. Okay, so in 2a and 2b, Let's see what the condition would be. Think of the domain of the original, or think of the range of the inverse, okay, for formula 2a. What's the domain of cosine? What did we restrict it to? Yeah. That's the range of the original. We're thinking for this, yeah, I want the domain of the original, not the range of the original. This is where we had to limit left and right. Yep. Yep. 0 to pi. Now, the -1 to 1 that you said, that's the next one. That's the range. Right. Now let's look at formula 3a. Domain of tangent. What did we have to restrict the domain of tangent to so that it passed the horizontal line test? Chris? That's range. That's range. So domain was when I drew the red bars like on the left and on the right. From this to this. Yep. -pi/2. Yes. It was where the vertical asymptotes are. And if you look quick, you might say, wait, isn't the restriction on 3a and 1a the same? No. 1a has less than or equal to's. 3a doesn't. Okay? So the restriction there is between -pi/2 and pi/2. And then what Chris said, the -infinity to infinity, that's the other one. So in other words, formula 3b always works. You can't pick a value for x that would make formula 3b false. It's impossible. Okay, so those are the actual conditions when an inverse trig function and a regular trig function cancel out. Now, just look at this one for a second. 0 to pi, that's radians. What would that be in degrees?
180.
0 to 180. Yesterday, since you guys were solving right triangles, your answer was always between 0 and 180. In fact, we could do even better and say it was always between 0 and 90. That's why this formula always worked yesterday. And that's why this formula always worked yesterday. Answers that you got yesterday automatically fit the conditions they needed to for the trig to cancel out. That's why I didn't have to explain what I just did right now. Okay, questions on that? All right, so transformations. I'm not really going to go into a lot of depth here because we just did this yesterday and 6 or 7 times before. But the transformations with inverse trig is exactly the same as everything we've studied all year. So I'll just ask you guys what the A, the B, the C, and the D would do. If you want to write it in your notes, you can, but you should already have it in there somewhere. What does the A do? Jared?
Left and right.
Yep, it's a horizontal shift.
Negative is to the right.
Negative would be to the right, positive would be to the left. Yep, that's A. What about B? Chris?
Horizontal shift.
I can't, that's 2 different things. So Jared just said that A is the horizontal shift, left or right. So then B would be, yep, that's the horizontal stretch to your graph. A big number for B actually compresses. A small number for B stretches. A and B are backwards. Okay, the way you think about it. What about C? Chris?
Vertical.
Yep, C is a vertical stretch, and that's what you would expect. A bigger number stretches it bigger, a smaller number compresses it smaller. What about D? That's your vertical shift, and that's also what you would expect. Positive is up, negative is down. What if B or C was negative? What does that cause? Yep, it would be a flip, either a horizontal flip or a vertical flip. Okay. So, if I give you a transformation, how do you find the new domain? Remember, domain is horizontal. The only two letters there that do anything horizontal are A and B. That's it. So, to find the domain of a transformation, you're going to create a compound inequality. Compound inequality looks something like this. You have to fill in 3 spots. The spot in the middle is going to be your argument. What's your argument? That's what's in the parentheses. Bx plus a. On the left and on the right is the original domain. That's what we just did in the notes. The original domain. So to find the new domain of an inverse trig function, put the argument in the middle. That's what's in the parentheses. And put the original domain on the left and on the right. Small number on the left, big number on the right. Okay, to find the range, what we're going to do is take into account any vertical transformations in that order. Stretch first, and then shifts. So, for example, let's say I had a domain that was 2 to 3. A range, 2 to 3. Let's say I stretch that range by a factor of 2. What would you get if you take that range and stretch it by a factor of 2? It wouldn't be from 2 to 3 anymore. It would be from, yep. From what? If we're going to do a vertical stretch by a factor of 3. Yep. Chris? No, it's going to get bigger. So the numbers are going to get bigger, but both numbers are going to get bigger. If you stretch this domain by a factor of 3. Yeah.
B6 and 9.
Yeah. If you stretch it by a factor of 3, your new domain is from 6 to 9. And now, what if you did a shift up 1? It would be from 7 to 10.
Shift up.
Because if you shift up, everything moves together, right? The lower part and the upper part, it all sticks together. So if you shift 6, 9 up 1, now you're at 7, 10. You get a new minimum and a new maximum in your range. Okay, so that's how you would handle the range. Okay. So we'll practice. We'll go through a few different functions, starting with inverse sine. So, find the domain of inverse sine 2x. Okay. What's the argument there? It's inverse sine 2x. Okay. 2x. So to find the domain, it says create a compound inequality with the argument in the middle. Right? 2x. Now it says to put the original domain on the left and on the right. Okay. What's the original domain of inverse sine? And if you get stuck and you're like, I can't remember the domain of the inverse, think of the range of the original.
Can you repeat that?
So I need to put the original domain on the left and on the right. What's the original domain for inverse sine?
Pi over 2. Pi over 2.
That's the range. That's going to be our answer next.
Negative 1 and 1.
It's -1 to 1. -1 to 1. Now, how would you solve that and get x by itself?
Alright, multiply everything by 2.
Then that would give you -2, 4x, and 2.
Or divide everything by 2.
Divide everything by 2. 2, 2, 2. What's my domain now? From what to what?
Negative 1/2 to 1/2.
Negative 1/2 to 1/2. Including or not including?
Include.
Yeah, including, because we got to equal to. So the domain, negative 1/2 to 1/2. Now, Jacob, how many transformations are happening in that inverse sine 2x?
Just one.
Just one. And that one transformation affected the domain. So what does that mean about the range in this problem? Yeah.
Doesn't change.
It doesn't change. There is no transformation here affecting the range, so you just need to tell me what the range is for inverse sine, and we don't have to do anything to it. So what's the range of inverse sine? Yep. Yes. Negative pi over 2 to pi over 2, and that is including. Okay. Let's look at this one. Inverse sine 1/3 x. Hey, Kaya, what's my argument here? Yep. So my argument is 1/3x. Put that in the middle. Now put the original domain on the left and on the right. We just went over that last time. It's -1 to 1. And now, Nakira, how would I get x by itself there? What did you say? You could divide everything by 1/3, which is the same as multiplying by the reciprocal, which in this case is 3. So let's just multiply by 3. 3, 3, 3. That's gone. So x is now between, Sam, x is now between what and what?
-3. Yeah.
Yep. Again, there's only one transformation in that problem. It changed the domain. So there's no transformation that changes the range. If the range is going to change, you're going to see numbers outside the parentheses. Okay. So it stays the same. Okay. Let's look at this one. Brandon, what's the +2? What kind of transformation?
Vertical.
Vertical shift. Vertical. Does that affect domain or range? Range. So the domain in this problem is not going to change. So all you have to do is write down your original domain. We've already said it in the past two problems. -1 to 1. Now, Brandon just said that it's a vertical shift up 2. So what's going to happen to my range is everything's going to move up 2. So what's my original range if I didn't move it up 2? Chris?
2 pi over 2 over pi bracket pi over 2 and pi over 2.
Yes. And you're going to take that and you're going to shift it up 2. There's not really a nice way to write it unless you're going to use decimals. I would just go like this. Negative pi over 2 plus 2. And pi over 2 plus 2. Okay. So we've done different transformations, but we keep doing inverse sine, inverse sine, inverse sine. I think I have a different one. Inverse cosine. Okay. What kind of transformation is that 5? Yeah. Vertical stretch. Vertical affects the range. There's no change in the domain in this one. So, what's the domain for inverse cosine? And you don't have to do anything to it. Helen? Yep. The domain is -1 to 1. Now, what's the range for inverse cosine? Just the original. Yep.
0 to pi over 2. Or
It is 0 to something. Pi. 0 to pi. You're going to stretch that out 5 times as much. So if you stretch out 0 5 times as much, what does it turn into?
0.
Stays 0. If you stretch out pi 5 times as much, what do you get?
Pi.
5 pi. Okay. So that's the idea of how you find the domain and range of an inverse trig function. Most of the time, I'm just going to give you one transformation per problem. So one of them stays the same, and then the other one changes. Any question on it? All right. So these are the last 2 things. In this one, I want you to identify the transformations. You don't have to tell me the domain and range. I just want you to tell me shift up, shift left, stretch, all that stuff. Now, there's something about this example that it doesn't look exactly like this. Does anyone see something you'd have to do first to make the example on the right look like what I've circled in red on the left? Eric?
Use the quarter through x plus 8.
Yes. We normally don't write it as parentheses inside parentheses like that. We should distribute out that 1/4 so we can see what A and B are. Okay. So we're going to get 1/4 x plus, what's 1/4 times 8? 2. Now you can see the A and the B. Okay. So we've got all the transformations here. We got A, B, C, and D. Just tell me what each one does. So there's 4 transformations. Okay. Caleb, what number would you focus on first?
The 2.
Yep, the 2. And can you tell me what the 2 is going to do to the graph?
It's not a bit bigger. I don't really know what.
So which spot is it in?
A.
It's in the A spot. Okay, so we know it's in the A spot. Can someone remind me, what does the A do? Yep.
Horizontal shift.
It's a shift. It's a shift and it's a plus. Which way does a plus go? Left. So all you want to do here is write shift left 2. How about Brianna? What's the next number that we would focus on? Yep, the 1/4 next to the x. That's in the b spot. About Chris, can you tell me what a 1/4 would do to the graph?
Horizontal stretch.
It is a horizontal stretch. Can anybody tell me by how much? Yep.
4.
Yes. That's one way to say it. Horizontal stretch by factor of 4. Now, technically, you could say shrink by 1/4, but that's kind of like using a double negative. That's like saying move down -2. If you said to move down a negative amount, that really means up. So I think it's more confusing to say shrink by 1/4. Just say stretch by 4. Okay, it means the same thing. All right, third transformation. Jacob, what number do I focus on for my third transformation?
3.
Yep, the 3, because that's in the C spot. Can someone tell me what does the 3 do to your graph?
That'll be a vertical shrink. Or vertical stretch by
Stretch.
1/3. 3.
3, vertical, don't mess with it. Just what you see is what you do. It's not the opposite. Vertical stretch by 3. And the fourth transformation, the only number left is the -5, and the -5 is going to move it down 5. So shift down 5. I'm not worried about sketching it on the calculator because I am going to ask you to draw something tomorrow for an inverse, but you're going to be able to use your calculator to help you draw it. And it's not going to be a problem that has 4 transformations in it. It's going to have 1. So I'm not worried about looking at 4. Okay, I might ask you to describe something like that, but I would not ask you to sketch something like that. Okay, and the last thing is just basically how do we type this in on a calculator? So first thing we got to remember is anytime we use inverse trig, and I've asked this question a couple times, you're always solving for a what? What did we use inverse? You're always solving for an angle. So that means if I give you a multiple choice question, you have to look at the multiple choice answers. They have the little circle. That means they're in degrees. You need to put your calculator in degrees. If you don't, you can keep your calculator in radians. Okay? Now, these aren't multiple choice. These are all short answer. So let's do them in degrees. Okay. Somebody tell me what buttons I have to press to do example A. Exactly, just button for button. Chris?
Second Sine. 0.5.
Enter. So in radians, the answer is 0.53. Yeah, it didn't, this isn't multiple choice, so it's not like they told you, let's practice. Yeah, they didn't say whether to use degrees or radians. But if you wanted it in degrees, I think I said I was going to do it in degrees. It's 30 degrees. Inverse cosine of -0.7. Second, inverse cosine, -0.7. That's it. 134.43 degrees. Okay. Inverse sine 1.2. What happened? How come when I typed in inverse sine of 1.2, my calculator says error? Yeah. It's over 1. The domain of inverse sine, we've talked about that, is -1 to 1. You can't plug anything else in besides that. So this one, you would just say no solution. Okay. And inverse tangent of 4.3, that gives you 76.91. So on the test tomorrow, if you forget, like, I don't remember how to do inverse, I'm not going to tell you how to do it, right? You have to do it the way I showed you. Like second, and then the trig button you need. Okay. Questions on it? All right. So anybody want me to go through what you need to know for the test tomorrow? Okay. So, test. Alright, so there are things on the test from each day. Okay? One thing you want to know how to do is find the period. Right? That's where we use the formulas pi over b and 2 pi over b. You need to look it up in your notes and figure out which one to use when. Solve trig equations. Okay. Something like sine of x equals 0.4. Now, with what I've just shown you yesterday, you guys could take the inverse sine of each side to solve it, or you just hand back in for me, Jerry. You could use your calculator, do a y1, y2, and see where they cross. You have multiple ways to do it. You should know how to find all solutions, specifically to a trig equation. That's where you put the plus period times n. So you need to know how to put plus period times n. Solve right triangles. That means if I give you sides and angles, you can tell me all the other sides and angles. That was yesterday. Find trig functions given a point on a terminal side. That's where I tell you, like, the point 3, 4 is on the terminal side. You draw the ray through 3, 4, and you make your little triangle, and that's where we did the reference angle stuff, right? And we did the sine, the cosine, the tangent, the secant, the cosecant, and the cotangent. We practiced all 6. What else? Use your calculator to do inverse trig. Okay, that's what we just went over today. Transformations. We just went over that. So you should know how something would be affected, up, down, left, right, all that stuff. And I am going to have you sketch an inverse trig function. And what I'll probably do with that is I'll have you sketch it, which you can pretty much use your calculator to help you, but I'll also ask you what's the domain and the range. It'll be a question like one of these. Okay. I'll ask you to give me the domain and range, and then I'll say draw a sketch. Okay, for the sketch part, you can use your calculator. Okay. but domain and range, you got to know how to figure out like we did. And I think that's pretty much everything that is on the test. That's everything. Okay, so that will be our last test for semester 1. Next academic week, we have the midterm on Wednesday. What else? I'll be after school today if anybody needs to stop by. And last thing is I work well. Okay. So that's the homework for tonight. Yes.
Are you gonna do it Tuesday?
On Tuesday?
Yeah. Are you gonna do like a review or are you gonna do it?
We're going to review on Tuesday. Yes. Yep. And I gave everybody the review sheet yesterday, correct? Okay.